Hello students, good morning. Welcome to my lecture for Class 12 Science, Subject Chemistry, Maharashtra State Board New Syllabus 2020. In the previous lecture, we have studied about D block elements, which are also called as inner transition elements. Now today we are going to study about A block elements. They are also called as inner transition elements. First we will see what are A block elements. See, elements in which last electron enters into the pre-penultimate shell, that is n-2f orbital, are known as A block elements, or they can also define as elements whose f orbital gets filled up by electrons are called A block elements. Now they include 28 elements with atomic numbers ranging from 58 to 71 and atomic number 90 to 103 collectively. There are two F series or two F block elements, namely 4F series and 5F series. Remember that. See, 6 period 4F series element, and in 7th period here 5F series element. 4F series elements are present in 6th period and 5F series element they are present in 7th period, and they are placed at the bottom of the modern periodic table. Now we'll see what are first inner transition elements. A block elements are known as inner transition elements, that we'll see. A block elements are called first inner transition elements and have partly filled inner orbital or n minus 2 f orbitals. Their general electronic configuration n minus 2 f 1 to 14, then n minus 1 d 0 to 1, and last one is what? N is 2. This is general outer electronic configuration. There are two F series, namely 4F and 5F series, called Lanthanoids and actinoids. Remember this. There are two series. First series is Lanthanoids and second series is what? Actinoids. They show intermediate properties as compared to electropositive S block elements and electronegative P block elements. Hence they are called first inner transition elements. Now we will proceed for what are lanthanoids. Now see, first we will see lanthanoids, the series of 14 elements from cerium 58 to lutetium 71, in which a differentiating electron or last electron enters 4F subshell and follows lanthanum is called lanthanoid series, and the elements are called lanthanoids. Their general electronic configuration, C xenon 4F then 5D 0 to 1, and last N is 2. See here, S is the last subshell, D is the penultimate shell, and F is what? Anti-penultimate shell or pre-penultimate shell. They follow lanthanum in 3D series. We will see position of lanthanoids. See, position of lanthanides in the periodic table. They belongs to group 3 and period 6. They interrupt. Now see, lanthanides belongs to third group and 6th period. They interrupt the third transition series of d block elements in the 6th period. There are 14 elements from cerium to lutetium, and their position is in between lanthanum and hafnium. Lanthanum and hafnium. See here, it is hafnium is given HF. Since they follow lanthanum, they are called lanthanoids. They are called 4F series elements, and for the convenience they are placed separately below the main periodic table. Actual position of lanthanide is in between lanthanum and hafnium. Their position is justified due to following reasons. All these elements have same electronic configuration in ultimate and penultimate shell, 1 electron in 5d orbital and 2 electrons in 6s orbital. Group valency of all lanthanide is 3. All lanthanides from cerium to lutetium have similar physical and chemical properties. Explain the meaning of inner transition series. That we will see. A series of F block elements having electronic configuration n-2 f1 to 14 n1-1 d0 to 1 ns2 placed separately in the periodic table represent inner transition series. Since the last electron enters pre-penultimate shell, these elements are called inner transition elements, and there are two inner transition series. One is what? 4F series. This is 4F series, and this is actinoid. This is what? 5F series. Now we will see important features of electronic configuration of lanthanoids. See, lanthanoids show two types of electronic configuration. One is what? Expected, and second one is what? Observed electronic configuration. Now let's see, there are two types of electronic configuration. One is what? Expected, another expected electronic configuration, and second one is what? Observed electronic configuration. Now see, in the idealized electronic configuration, the filling of 4f orbital is regular, but in the observed configuration, there is the shift of single electron from 5d to 4f subshell. Lanthanum has an electronic configuration xenon 4f0 5d1 6s2. It doesn't have any f electron. The next incoming electron does not enter the 5d subshell but goes to the 4f subshell. 14 electrons are progressively filled in the 4f subshell as the atomic number increases by 1 unit from lanthanum to lutetium. Lanthanum, gadolinium, lutetium are the only elements which possess 1 electron in 5d orbital, which in all other lanthanoids the 5d subshell is empty. So in your table 5d subshell is not written because 5d subshell is empty. Now see, lanthanum, it has 4f0, gadolinium, it has 4f7, and lutetium has 4f14. Possess extra stability due to their empty, half filled and completely filled 4f orbital respectively. The 4f electrons in the pre-penultimate shell are shielded by the outermost higher orbital, that is 5s2, 5p6, 5d1, 6s2, that is by 7 electrons, hence they are less effective in chemical bonding. Now you revise this table, we will get the idea of electronic configuration about lanthanoids. Moderate densities of about 7 gram per cm cube. This is the first property. They have high melting and boiling point. High melting means their melting point is what? 1000 degrees Celsius, and boiling point it must be around 3000 degrees Celsius, which is similar to group 1 and 2. Lanthanoids are very reactive and resemble alkali and alkaline earth metals because they show some similarities with alkali and alkaline earth metals in their reactivities than transition metals. For example, they react with water. See, metal plus water, they can form what? Hydroxides, along with evolution of what? Hydrogen gas. Now the common oxidation state for lanthanide is +3 and +2. Before that, you must know what is meant by oxidation state. Oxidation state is the total numerical charge assigned to the atom of an element in a molecule. The common oxidation state of lanthanide is +3 due to loss of 2 electrons from 6s orbital and 1 electron from 5d orbital. Some lanthanoids show +2 and +4 oxidation state because they lose 2 or 4 electrons and acquire stable electronic configuration of 4f0, 4f7 or 4f14. Some lanthanoids show +2 and +4 oxidation state even though they do not have stable electronic configuration of 4f0, 4f7 or 4f14. See here, they all form stable oxides, that is what? M2O3. M represent lanthanides. M2O3, you get what? We can consider 4Ln, that is lanthanides, plus 3O2. Here you get what? 2Ln2O3. That is what? Lanthanoid oxide. Now similarly, lanthanide can react with what? Reacts with what? Nitrogen. See here you can get 2Ln plus N2, you get 2LnN, that is lanthanide nitride. Similarly, lanthanide can react with what? Halogens. So here we get 2Ln plus 3x2. What will you get? You get what? 2Ln x3. 2Ln x3. That is lanthanide halide. Similarly, lanthanide can react with what? Carbon. Means here you get 2 lanthanides plus 3 carbon. Heat, you get Ln2C3. Ln2C3. Properties of lanthanoids. These are very simple. Soft metals with silvery white color and moderate densities of 7 gram per cm cube, and color and brightness reduces on exposure to air. Means when they are exposed to air, their color and brightness reduces. Reduces means what? It will be decreased. They are good conductors of heat and electricity except promethium. All are what? Non-radioactive in nature. Means what? Promethium is what? Radioactive in nature. The atomic and ionic radii decreases from lanthanum to lutetium. This is known as what? Lanthanoid contraction. Similarly, binding to water is common, such as water is often found in products when isolated from aqueous solutions. Means they can react with what? Water. Paramagnetic. Lanthanides are strongly paramagnetic, means they contain unpaired electrons. Gadolinium becomes ferromagnetic below 16 degrees Celsius, which is called as Curie point. The other heavy lanthanoids, terbium, dysprosium, holmium, erbium, thulium, and ytterbium, become ferromagnetic at much lower temperature. Now see, magnetic and optical properties are largely independent of environment. Similar spectra in gas, solution, solid. Now we will study color of lanthanoids. Now see, the color of lanthanide ion depends upon the number of unpaired electrons. Lanthanide ions exhibit color due to FF transition, that is transition of unpaired electron from f orbital of lower energy level to the f orbital of higher energy level. The color of lanthanide ion is due to the absorption of light of certain wavelength and transmission of light of other wavelength in the visible region. The colorless lanthanide ions absorb and transmit light either in the UV or IR region. Lanthanide ions having equal number of unpaired electrons have similar color. The color of lanthanide ion, that is lanthanum plus 3 to ytterbium plus 3, are similar to those of 7 elements deuterium 3 plus to terbium 3 plus in the reverse order. This is about what